Yep.
Right. Okay. Assalamualaikum. Good afternoon. Thank you everybody for joining. So I see quite a few students already online. So maybe a bit of introduction. So today I believe the adjunct lecture will be as touching on the topic of SIS. But I sort of renamed the topic to Fundamentals of Functional Safety and IC 61511. This sort of two topics are somewhat related, um, to safety instrumented systems. Before I proceed, just maybe a show of hands. If you can raise up your hands. How many of you are from the industry, have industry experience? Nabila, Fahad. Okay, Fahad's from industry. The rest? Are you guys straight from degree? Okay, already in. Okay, maybe Fahad, maybe start with you. Maybe just for me, just to gauge what are your industry experience like so far?
Yes,
Yeah.
Doctor. I do have an experience with the power and water sector. As I work as operation and maintenance
Mm-hmm.
engineer. Later on, I was assigned to be an health and safety manager for almost last 12 years. So in the total 18 years of experience in power and water sectors, including renewable energy and then also other management skills.
Great.
So from safety perspective, I do have a good alhamdulillah experience as well. I graduated or I completed the certification, which is like available in the industry, which is like NIBOSH diploma, international diploma,
Mm-hmm.
NIBOSH environment, NIBOSH process safety, and other relevant OSHA training from NASP. So those all, alhamdulillah, I have completed. ISO 45001 lead auditors and also environmental lead auditors 14001 I have completed also.
Great, great, very experienced. All right, that's good to know. How about yourself, Fahrudin, is it?
Yes, thanks, Fashion. So I'm around 7 years working experience. I'm from Indonesia,
Mm-hmm.
10 within the process safety. So now I'm working for the Cargill as the process safety lead, covering sub-regional Indonesia and Australia and New Zealand. And previously working for the BP, British Petroleum, in one of the LNG plant in Indonesia. In terms of the related for the SIS or functional safety, I got my certification for CFSP, some functional safety professional
Mm-hmm.
from the Exida on the
Mm-hmm.
2014. And last couple of years, I get certified for the CCPSG, certified safety professional from the CCPS.
Oh, great, great. So
That's
maybe
it.
some of the stuff today will be nothing new to you, Fahrudin. Some of the things
Thanks.
today may be a refresher for you. So you said you're from currently with Cargill, right?
Yes, currently with Cargill. Yeah, yeah.
Okay, okay. All right. Anybody else from the industry would like to share their experience? Nabila? So,
Hi,
hi.
I'm new to industry actually. I'm just
Ni.
currently doing for fire safety. Just assist my supervisor in oversee their FPS and ITM schedule, the fire safety program on the operating unit. That's all.
Okay, all right. No worries. Great. Great to have you today. How about Kai? Kai Ji Yao.
I just only recently starting to work. Actually, I joined masters after my degree straight away, and
Okay.
I'm in consultant in safety wise lah. Yeah.
Okay. Okay, great. And I think we have one more. Ali, is it?
Yes, good afternoon, Ali Jadad, TC manager. I'm working in power sector since 2008. I take responsibility for safety since 2015. So I have Nibush, IGC, process safety, and other
Mm-hmm.
training.
Great, great. Okay, all right, all right, good. There's some experience, guys, in this call, and there's some fresh graduates newly into the workforce. So okay, maybe I'll start with my introduction. So my name is Fashan. So I'm actually a UTP graduate. I graduated in 2009. My experiences mainly is in the oil and gas sector. I started as an instrumentation and control engineer in a refinery operated by Shell here in Malaysia in Port Dickson. And then from there, I moved on to chemicals. I went to work on with BASF, Chemicals in Giving, where I was the Functional Safety Technical Authority, and the SIS Technical Authority. And currently, I'm sort of the consultant also in the realms of safety, risk, and reliability, based in Malaysia, based in Seremban actually. Right. I'm a professional engineer in the areas of instrumentation and control. Certification-wise, I went to the TOV course in 2013. I was also the former IPF focal point for Shell refinery in Port Dickson. So tackling day-to-day issues with SIS or IPF related issues. Okay, it's a bit about myself. So I guess the agenda for today will be a bit of in 2 hours. Hopefully, I'll cover some topics in the areas of functional safety. Some of you might be wondering what is it all about. Touch a bit on the IEC standards, the 61508 and 61511. What are SIF loops, failures and reliability, SIL or IPF classification, and then the testing and maintenance, right? So quite a few topics to cover in 2 hours. So let's see where we land. If there's questions, you can put the questions in the chat. Maybe after lecture we can answer them together. Okay. So for us to understand safety systems and functional safety, we need to understand the history, or we need to learn from the disasters that has occurred that led us to requiring functional safety, right? As far back as 1976, we had a massive catastrophic incident in Seveso, Italy. Some of you may have heard this, where there was the large amount of dioxin release, right, after an explosion. There was a large area contaminated, eventually and unfortunately leading to a lot of people suffering from various diseases, right? It was in the 1970s. And not 10 years later, in 1984, again, we had another catastrophic incident happening which happened in Bhopal, India, where in that disaster, 40 tons of methyl isocyanate released after an explosion. And I know that it was an estimated casualty of up to 25,000 people were killed as a result of the disaster, right? There are a lot more disasters, some of it very recent as well. But what do these disasters impact how we operate? Okay, so these incidents made the world reconsider the safety approaches, especially when it concerns people and environment, right? So the IEC in turn published the functional safety standard, IEC 61508. Okay, and in Europe, there was a standard called the Machinery Directive, which is a legal requirement for machinery safety. Okay, so this IEC 61508, you will hear quite a fair bit of it being referenced to, especially in the areas of safety systems and functional safety. So how does the IEC 61508 relates to the other sector-specific standards? So the 61508 is of the mother standard, and from which there are sector-specific standards developed. Like for example, the IEC 61513 for the nuclear sector. 62061 is for the machinery sector, and 61511 for the process safety, process industry sector. Okay. So our reference today, or we'll be talking a lot about 61511 for the process industry sector, right? Which covers petrochemical plants, refinery, and so forth. Right. So in terms of relationship between these two standards, 61508 is mainly the standard used for manufacturers or suppliers of safety devices. This would be companies like Yokogawa, or companies like Emerson, or companies like Schneider Electric, who produces equipments used for the safety instrumented systems. In turn, the 61511 is mainly for system designers, integrators, and end users, right? So it's related, but in terms of its application and usage, is somewhat different. Okay. So the 61511 scope, again, it covers process industries. This includes chemicals, oil and gas, paper, pharmaceuticals, food and beverage, and as well as non-nuclear power generation. It does not include embedded software, and again, it's intended for use for end users and system integrators. We'll be covering a bit later the lifecycle management, but it's essentially it covers the 11 phases within the functional safety lifecycle. Okay. So if you look at the 61511 standard, this is the safety lifecycle most often referenced when you talk about safety systems, right? It covers analysis, right? This is where you do your hazard and risk analysis. You do your allocation of safety function to protection layers, and as well as the safety requirements specification for the SIS, right? So the analysis portion is mainly done mostly as a desktop work. Right? The second phase is the implementation. So once you do your analysis, you've done your hazards, you've done your C allocation, you've developed safety requirement specifications, and now it's to realize it into a system, right? So this is where your engineering comes in, where companies come in and design the safety systems themselves, right? And also involves the installation and commissioning as well as validation, right? Not only do you need to design the safety system correctly based on the analyzed hazards, but you also need to install, commission, and validate that it's installed correctly, right, as part of implementation. Okay. The operation phase, right, of the safety life cycle includes operation and maintenance, modification, and decommissioning. Arguably, the operation phase is one of the longest phases in the life cycle, right? So this is where you operate and maintain your safety systems throughout the life of the plant itself, right? Can span over many years, right? So my previous plant, for example, my refinery was built in 1960s. Right, you can imagine some of the safety functions has been in that operation phase, for at least 30 to 40 years. Right? Okay. So this is also one of the hardest phase also to maintain. All right. So what is functional safety? So the functional safety is detection of a potentially dangerous condition resulting in an activation of a protective or corrective device or mechanism to prevent hazardous events arising or providing mitigation to reduce the consequence of the hazardous event. Right. So this is the IC definition. Right. So in short, it's about detecting potentially dangerous condition, and you activate a protective or corrective device, right, so that you can prevent the hazard from arising. Right. It's an automatic function. Okay. Right. So the real challenge is to design the system correctly. Right? What standards do we need to follow? What are the things that we need to consider? Okay. There's always this balance, especially when you're operating a plant, about safety versus availability, right? And the mantra is always safety first, right? So there's you want to make sure that at the end of the day, people go home safely. You want to safeguard the environment. You want to safeguard people outside the plant, your community surrounding the plant, right? You also want to safeguard the people inside the plant. But at the same time, plants are there as a business, right? So there's also the interest to put availability first, right? A running plant, therefore, is able to run and make profit. It's about protecting your production, protecting your asset, making sure that your products are on spec, as well as maintaining that corporate image, right? So it's about balancing these two, right? Between safety and availability, and that's where doing risk assessments and balancing risk is important, right? Okay. Right. So there will be a few terminologies that will be used repeatedly throughout the lecture. SIS, SIF, and SIL. So SIS, SIF, SIL. Okay. So SIS is a safety instrumented system. SIF, SIF is safety instrumented function, and SIL is safety integrity level. Okay. So a lot of abbreviation, a lot of short forms. It gets easier with time, right? Often, more often than not, even for me, I confuse and not confuse. I interchangeably use the different terms, right? But yeah, so safety systems, safety instrumented functions, and safety integrity level. Okay. So what's the difference between these three? So a safety instrumented system is a set of devices and software that perform one or more safety functions, right? Right. So there's a system, right? It performs multiple safe functions, right? So it's a sort of a subset of a SIS, right? So each safety function, each SIF has a stated safety integrity level, right? So each SIF will be assigned a targeted SIL, SIL 1, SIL 2, or SIL 3, or SIL dash, right? That is related to the probability that the SIF will not work when demanded to, okay? So again, let me repeat that. So a safety system is a set of devices and software that is performing one or more safety instrumented functions, and each function has a stated safety integrity level. Okay. So safety instrumented functions, SIF, right, is a set of equipment intended to reduce the risk due to a specific hazard, right? So its purpose is mainly to automatically take an industrial process to a safe state when specified conditions are violated, right? So for a SIF, when you design a SIF, you set conditions, right, for which if met, it will take automatic actions, right? Whether the temperature high or temperature low, pressure high, pressure low, and so on. Okay. So when the conditions are met, it will automatically take action to bring it to a safe state. Okay. The second purpose is to permit a process to move forward in a safe manner when specified conditions allow. This is for things like batch processing, for startup sequence, and so forth. Okay. The third action is to take action to mitigate the consequence of an industrial hazard, right? Okay. So again, there's preventive, there's mitigative, right? So mitigate the consequence of industrial hazard, right? So it includes elements that detect an accident is imminent and decide to take the action and then carry out the action needed to bring the process to a safe state. Okay. So all this purpose, right, the ability to detect, decide, and act is designated by the SIL. Okay. Right. So different SIL levels will require different probability of failure on demands, different requirements, different design requirements, right, in terms of designing it to take that automatic action. Right. So again, remember that each SIF has a designated SIL, safety integrity level. The safety integrity level is one of 4 levels, right? So each corresponding to a range of target likelihood of failures of a safety function. Okay. So if we look here, right, there's the different SIL levels starting from SIL 1 to SIL 4. Right, SIL 1 being the lowest and SIL 4 being the highest SIL. Okay. The difference here between the SILs is the average probability of failure on demand, or you can look it from the other way is from the risk reduction factors. Right. So basically for a SIL 1 function, okay, the probability of it failing is between, right, 10 to the minus 1 to 10 to the minus 2, right? Layman term means to say that the probability of it failing is between 1 in 10 times to 1 in 100. Right? If you go to SIL 2, right, it's a factor of 10. So the likelihood of it failing is 1 in 100 to 1 in 1000. And SIL 3 is between 1 in 1000 to 1 in 10,000. and sulfur is 1 in 10,000 to 1 in 100,000. Right, so likelihood of failure. Okay. Right, if you look at in terms from availability, it's about how many nines are behind it, right? So 0.9 to 0.99, right? So availability is at sulfur is highest at 99.99%. Right. Okay. All right. Okay. So SIF loop, right? We've mentioned before that a SIF loop has a still level and is made up of components, right? So there's three main subsystems within a SIF loop, which is the sensor, logic solver, and final element. Right? So what is a sensor? So sensor is basically your transmitter in the field. So it's senses an abnormal process condition and represent a potential hazard, right? So this can be your pressure transmitters, temperature transmitters, flow transmitters, right? The sensor, and then you have a logic solver, which based on the input from the sensor, activate a defined executive response to hazardous event, right? This is sort of the brains of the function, right? So it takes it processes it, and it executes an output. Right? So final element is activated to prevent or the hazardous event or mitigate after event consequences. So final elements can be items like valves, motor trips. Right. So if I were to put an analogy to this, is that if you your sensor, if you compare it to the human body, the sensor will be your 5 senses, right? Your eyes, your hearing, your sense of smell, your sense of touch. Okay, the logical processor, the logic solver will be your brain. So you take that input in, right? If you see a car coming, speeding, barreling down towards you, right? Your eyes take it in, your brain thinks about it, right? So what you should do, right? And then the final elements, and then it decides that either you need to move away or you need to run or you need to jump out of the way, right? So in terms of final elements, this is your legs and feet. That actually are your muscles that's moving you out of harm's way. Okay. All right. So let's look at this quick example of this typical setup. Okay. You have a vessel here. You have hydrocarbons coming in, right, at about 120 bar. On the top, you have a RV with a high protection and a pressure control coming in to this pressure control bar. On the vessel, there's also a level control loop, right, maintain this level here. So based on this diagram, schematic, which would be the sensor for the safety function? Any takers?
Again, sir?
Which okay, if we looked at this diagram, right? Which of these elements in the diagram is a sensor for a safety loop, do you think?
High pressure transmitter for high leading to for closing interlock supply system.
Right.
It's
Great.
the market, right?
Okay. So this is the sensor. Final elements. Anybody? I'll take guess.
PZA002.
Right. PZA is this final element, and that would make this block here sort of the logic solver. Okay. Right. So yeah. Brian, thanks for that. So yeah. So the typical safety loop would be then in this example here would be your pressure high. Okay. Your pressure control will be a control function. This will be the sensor. This is what will be detecting the pressure, right? Measuring the value, and then depending on the set point, tells you that the pressure may be exceeding the prescribed safety conditions. And then the logic solver here will compute, right, and decide that okay, I need to de-energize or I need to close this valve, and de-energize the solenoid, and we'll close this valve here 01 PZA002. Okay. Right. Thanks for that, Faradin. Okay, and so it's open. Okay, so for sensors, for those of you who have had field experience, probably you've seen this before. But for those who have not had that field experience, sensors can be analog sources, such as pressure, temperature, level, flow. If you look at the pictures here, this will be some examples of some transmitters that will be installed in an industrial setting. Right, this can either be a DP type or pressure type, or can be used for flow. This will be. Anybody would like to guess what this sensor is measuring?
This
It seems like thermocouple, huh?
Thermocouple. Right. So this is for your temperature elements, right? Measuring temperature. Right. So what the sensor does is actually converts physical values, right? So you have physical value of of flow, of pressure, of temperature, right? Right, detected, right, from the sensor, and you need to send it to the logic solver in a standard or standardized value. So typically, it's using 4 to 20 milliamp current. Okay, right. So this is an industrial standard for most industrial systems now. In some cases, there will be sensors that's using discrete inputs. Discrete meaning is either on or off. For example, valve position limit switches, pressure switches, hand switches. Although it's uncommon, there are some plants that's still using discrete inputs for safety functions. Okay. Then logic solvers takes the input from the sensors and make the appropriate executive decisions to change the outputs, right? Depending on how you configure the logic itself. Right? If you say that, for example, if you can configure a logic just now on high pressure, instead of closing a valve, you want it to open a valve. Right? It can be done, right? It's usually fine. It depends on your specification on what's the hazard and what actions can you take to mitigate the hazard. Okay. So a lot of the modern logic solvers are now electronic-based hardware. So you have your, with the advent of microprocessors and all that electronics. So a lot of the PLC that you see in the market now is all electronic-based, right? But in my old plant in PD, some parts of the plant was built in the 1960s and the hardware was migrated in the 1980s. So they were still using wired logic. So there are still some plants that's using hardware logics, but most newer plants now are using electronic-based PLC for their logic solvers. Okay. Right. So again, finite elements. So action element required to prevent or mitigate the hazardous event. Anybody want to guess what? Or anybody know what this is? Or Nabila, have you seen this? Do you know what this is?
Flow. It's flow device, which is I think flow meters.
Not quite. Not quite.
It's a valve, pneumatic valve.
Yes. Yeah. So yeah, it's a pneumatic valve on a valve. Right. So one example of a finite element. Okay. Right. So the finite elements here is the thing that acts for you to mitigate or prevent the hazardous event. Right. It can be valves, it can be solenoids, it can be motors. Right. It's important for you to identify the appropriate finite elements that are critical to prevent or mitigate the hazard. Right. For example, in our case just now, if you want to prevent high pressure, right, closing this valve will stop the feed going into the vessel itself, which will be sufficient, right, to stop the high pressure scenario, right. You don't want to put yourself in a situation where there's high pressure and you want to say, I want to close all the valves in the system, right. I want to close this, and this, right. Whereas closing one will be sufficient. Okay. Right. So it's important to identify the finite elements that are critical to prevent and mitigate the hazard. Right. Certification of equipment. So the IEC standards does require you to select components that is capable to meet the target safety integrity level. Okay. meaning to say that if you assess that a particular function needs to meet a SIL2 safety level, safety integrity level, then it's important for you to demonstrate that the device selected, the sensor, the logic solver, and the finite element is capable to meet that target safety integrity level. Okay, one way is to use certified equipment, right? So evidence of systematic capability. An example here, if you buy equipment that's already specified to use, safe for use for in safety function, it will typically come with documentation to say that it's SIL3 capable, right? If you look at systematic SC3, SIL3 capable. What it essentially says that you are able to use this device up to a SIL3. Okay, that's one method of getting certification. The other method is there's also the prior use justification, but that will require historical data and operating experience for you to justify equipments without evidence that end users can sort of justify the use based on the maintenance history, right? So for example, they have equipment that have been operating in their plant for the past 20 years with no problems, right? There's also avenues for end users to justify that for use in a safety system. Okay. All right. Not sure, Faridin, have you had experience with prior use justification?
Yeah, that's actually sounds like it doesn't have the formal certification from the third party, either Exida or TUV, but somehow we have the internal record in the past. We are running quite a lot of experience, and in the past there is in terms of the failure rate, but somehow prior to use is prone to be difficult to for what we call
justify.
Justify. Yeah, yes.
Yeah.
Very difficult.
Yeah. I think there's a lot of debate on prior use. But that's a separate discussion altogether. Right. So the easiest route is just to get the equipment with the cert.
Yeah.
And everybody sort of agrees. Okay.
Some political in terms of the budget it be.
Yes. Okay. All right. So that's safe. So then some of you may be wondering, so how do I determine, right, what SIL level is required for the function, right? Whether it's SIL1, SIL2, SIL3, right? Okay, so next we'll go through SIL determination through qualitative method. Okay, so SIL determination, there's a couple of methods for you to determine what's your target SIL. Right. So in the life cycle analysis, in the safety life cycle, it's actually here, allocation of safety parameter for protection layers. So this is where you sort of do your safety integrity level workshops, right? Using either a qualitative method or semi-quantitative methods or purely quantitative methods. Right? Example of a method that you can use is risk graph. So it's somewhat qualitative or semi-quantitative. Risk matrix, qualitative, and also some semi-quantitative. There's also layers of protection analysis, semi-quantitative, and there's fault tree analysis, which is a fully quantified method approach for you to determine your target SIL. Right. Maybe show of hands, quick show of hands. Anybody? How many of you have done risk graphs before? Or risk graphs? No. Risk matrix? Okay, no, right. LOPA, maybe some of you have done LOPA. Right? Or then, okay. Okay. FTA, maybe not a lot. Right. Okay. So popular methods is currently LOPA. But there are some organizations that use a hybrid between risk graph and LOPA. We need to say they use risk graph first, and then whichever functions result in a SIL2 or higher, then they bring it forward to a LOPA session. to do a more detailed analysis. Okay, so what's the difference between all this approach and why is it so different? How are they so different? Okay, we'll go with that a bit later. Okay, so what's important even among the different methods is the assessment team. Okay, so regardless of the method used, it's important that the assessment team composition should consist of experienced personnel. Okay, so it is not a silo work when you do SIL assessments. It has to be done with the correct mix of experiences and expertise. Typically, it will include a facilitator, somebody who will facilitate the workshop. You also need a process engineer, somebody who is very well versed in the process being assessed. You need an instrumentation and control engineer, right? Operation and maintenance, process safety, and discipline engineers depending on the package. Right? Sometimes you will also need to call upon rotating equipment engineers or static engineers or corrosion engineers. But these are typically as and when required. Okay, right. So again, it needs to be a fair mix of experienced personnel as well as different disciplines. Right. If you don't have the right mix, you might end up doing being too conservative or not doing enough. Okay. Right. So one thing common about all these methods is that whenever you do SIL classification or SIL target, is that you need to describe the design intent. Right. So describe the hazardous event being averted. Right. A hazardous event is a situation with the potential to cause harm to people, environment, asset, and reputation. Okay. So you want to make sure that you're specific with the design intent, right? Not describe the consequences. For example, you can a function is there to prevent a compressor 1000 K1000 damage due to liquid carryover from V2000, right? Okay. Or you might one example as we saw just now is to prevent high pressure in V100. Okay. So it's important that we describe the design intent. Demand scenario, right? We also need to describe how the failures develop, right? The initiating events and how it leads to the demand on the SIF. Okay. Right. For example, if the high pressure just can be due to a pump tripping, you need to describe that the pump is stopped, or if there's a factor of human error, or there's a human failure, or if there's a failure of a control function. Okay. Ideally, you also describe in the demand scenario what other layers of protection will act when the SIF fails on demand. Right? If there's a another control that will take action. Okay. All these demand scenarios typically you will use in LOPA, and you identify use it to determine the intermediate risk. Okay, which is the risk without the SIF, but with all other layers of protection. Okay, it's important that you also write this down when you do the SIL target workshop. Okay. Right, consequence. So consequence is describing on how the events will ultimately lead to the consequence, right? Okay. So it's important that you focus on the potential credible consequence, right? Realistic worst case. So this is where having a good mix of experience in the assessment team will help. Okay, for those without the necessary experience, they might not be able to imagine the more potential credible consequence, right? Right. You know, and you don't want it to develop such that worst case is that the vessel will explode by an explosion, and then nuclear disaster, and it goes on and on, right? So you want to make sure that the consequence here is credible. Okay. So if the consequences are potentially not credible, describe the mitigation action that should be taken into account. Okay. For example, here there's an example here. Right, if there is a vessel explosion, right, there's vapor release, right? So consequence will only occur if the vapor cloud ignites, the explosion only if the vapor cloud ignites, and the probability of ignition is expected in less than 1 out of 10 cases of release. Right, meaning to say, if there is a vapor release, flammable gas release, probability of it igniting is 1 in 10 cases. Okay, so the likelihood of ignition also depends from company to company. Right, so each company will have its own standards and its own specifications on when to take conditional modifiers and how you take probability of ignition. Okay, so the other thing to consider when doing this is process safety time. Is how fast should the SIF act, right? From the moment the hazardous situation is detected until the hazardous event occurs, right? So this process safety time is the time between the hazardous situation is detected and, for example, and high pressure, between high pressure and explosion case, for example, right? Why this is important is that you want to make sure that the automatic action, right, the SIF has enough time to react. Okay. For example, if you say that between your high pressure and your vessel exploding, right, the pressure buildup can be as fast as 5 seconds, for example. But then when you look at your SIF, your SIF response time is 10 seconds, right? So that means that your SIF is unable to respond, right? Fast enough, right? That might require some redesign on the SIF function. So SIF response time is a determination of the process requirements concerning the response time of the SIF to achieve the safe state of the process, right? So your sensor itself is not going to act immediately, right? So for example, temperature, right? So when there's temperature build up, the temperature sensor might take up to a minute for you to detect the temperature build up, right? For the metal to heat up, thermal well to heat up. Okay, so there's a sensor response time that needs to be considered. Even for pressure transmitters, right? It's not going to be immediate. There will be some lag, 1 second, 2 seconds. Okay. The logic solver also, it needs some time to think about it, right? So when it detects the input from the field, it needs some time to process and then decide the course of action. Sorry. And then there's also the final element response time. Right? If you imagine valves, if you ask it to close, it will take a few seconds depending on the size to close, right? Some will say that the rule of thumb is 1 inch a second, right? So if you have bigger valves, then it will take longer for it to go from fully open to fully closed, or from fully closed to fully open, right? So the total response time, right, for the SIF needs to be faster than the process safety time. Okay. Yeah, right. Right. So again, let's look at SIF determination. So again, if you remember, there's risk matrix, risk graph, LOPA, and FTA. So let's look at risk matrix, right? So what is risk matrix? Some of you may have seen this matrix. So it's basically a matrix between consequence severity and likelihood. All right. So for some companies, what they've done, they have generated a calibrated risk matrix, right? So when you discuss on consequence, like I mentioned earlier, so among the items you discuss is consequence, right? So based on the consequence, they then decide what's the severity. For example, to people, will it lead to no injury, or will it lead to fatality, or will it lead to permanent disability? Okay, that's on the consequence severity. Then they will also, as a team, discuss the likelihood. What's the likelihood of it happening? Right, pressure high or overpressure and all that. Right, depending on experience, is it 1 in 15 years, 1 per 20 years? Right, depending on the demand scenario, right? So you discussed demand scenario earlier. So what will be the likelihood of it happening? Okay, so based on the likelihood and the consequence, right, they have already assigned the target seal. Right? If you say, for example, that the consequence can lead to permanent disability, you might lose a foot or lose a hand, right? But the likelihood is 1 in 1 to 5 years, then the function needs to meet a minimum of SIL1. Okay. But if the consequence is, for example, can lead to somebody dying or killing somebody, fatality, and the likelihood is also 1 in 1 to 5 years, then it will be a SIL2 function. Okay. Bearing in mind, so this risk matrix is company specific or organization specific. Each company will have their own calibrated risk matrix, right? So this, for example, if this is a 4x4, some will have 5x5 risk matrix, some will have larger risk matrix. Okay. So risk matrix is somewhat easier to execute in terms of determining the SIL, but it's a bit harder for you to calibrate, right? How do you know that this is the one and this is not required and all that? So a lot of justification is needed to qualify that which sectors require, which quadrants in the risk matrix require a SIL or not. Okay. So the other method here is the risk graph. So risk graph is it will look something like this, right? So there's a few parameters that you need to consider when doing risk graph, right? There's the consequence parameter C, right? Remember earlier we talked about consequence. So once you documented your consequence, right? It will be used to determine the consequence parameter. Exposure time parameter, which is the F, right? P parameter, possibility of avoiding hazardous events.
Mr. This look like inventory, huh?
Yeah. I've not seen inventory, but I think it looks like a lot of trees, fort tree and root cross trees. Yeah, it's somewhat similar, somewhat of a similar concept.
Yes.
Right. And the other parameter that we need to consider is the frequency of the hazardous event in the absence of failure of the SIS, right? So this is the W parameter, right? Okay. So this risk graph in itself will not help you, right? Because you don't know, you will not know how do I choose CA, CB, CC, or CD, right? There's the 4 different branches, right? So whenever a risk graph approach is used, a definition is required. For example, the C parameter, consequence parameter, right? Okay, depending on the consequence, you need to then calculate whether it's CA, CB, CC, or CD, whether it's this range from 0.05 to 0.05, 0.05 to 0.5, or more than 0.5 up to 5.0. Right? Calculating this, so based on this description, in this example, is that you based on the consequence. If you say there's a small release of flammable or toxic material, then V equals to 0.01. If it's a large release, 0.1, right? But if it's a large release, but also a high probability of catching fire or highly toxic is 0.5. But if your consequence you say that there's a rupture and explosion, then V equals to 1. Okay. Right? So consequence is basically this number is calculated by determining the average number of numbers present when the area is occupied and multiplying by the vulnerability of the exposed individual to the identified hazard. It is this number multiplied by the average number of people present in the area when the area is occupied. So if you say there's typically two operators in the field around the equipment during a normal shift, and there's a small release of flammable gas, flammable or toxic material in the worst case consequence, right? That is 0.01 times 2. Okay, and you will be somewhere CB. Okay, so this needs to come with the risk graph. And again, this can be this is an example. So each company will have its own descriptors for the consequence parameter. Okay, so the other parameter is the personal exposure, right, of occupancy. So it's calculated by determining the proportional length of time the area is exposed to the hazard is occupied during normal working period, right? Okay, so in this example is calculated by the total number of hours the area is occupied divided by 8760, which is the number of hours in a year. So if you say that the area is typically occupied by somebody, 12 hours per day, right? Every day, or sorry, not 12 hours, 2 hours per day every day. Then you take the total number of hours divided by 8760. From there, you will then determine whether it's a rare exposure, meaning to say that if occupancy is less than 0.1, right, less than 76 hours per year, right? So, or if there's a frequent to permanent exposure in an area where occupancy is more than 0.1. Okay, so this will determine your exposure probability, right? The other parameter is the probability of avoiding the hazardous event. Remember when we discuss the consequence, we also discuss what other safeguards are in place. Okay, so it says here there's PA or PB. So selected only if all conditions are satisfied. But the conditions could be facilities are provided to alert operator that the protection has failed. And there's alarm to tell you that the protection has failed. Independent facilities are provided to shut down such that the hazard can be avoided, which enable all persons to escape the safe area. Right, there's independent safeguards other than the safety function provided. Right, maybe there's other interlocks or maybe there's other safety functions, right, a different safety function. And the time between the operator being alerted when the alarm comes on and hazardous event occurring exceeds 30 minutes, right, or is sufficient for the necessary action. Okay, and to say if there's an alarm that is supposed to alert the operator has more than 30 minutes to respond, right? So in this example, if all these conditions are met, then you can select PA. Okay, right. So you need to consider things like operation and supervision of the process, right? How quickly the hazardous event develops, right? Quickly or slowly, again related to process safety time. Okay, right. How easy is it to escape? Okay, right. So then you can select whether it's either you can select PA or PB. That's almost impossible to avoid the event. Okay. So demand W, the last parameter, is the number of times per year that the hazardous event would occur if the SIS was not installed. Right. So if the SIS is not there, what would be the demand rate of the hazardous event? Okay. Right. Considering the initiating event, the demand scenario, considering all other safeguards in place other than the safety system, right? What would be the demand rate? Okay. Right. So W1 is again 1 in 30 years, or between 1 in 3 years, or between 1 in 3 years to 1 in 4 months, right? But again, this demand rate, this band will depend on companies from each organization will be different. Okay, but the intent of this parameter, right, is to estimate the frequency of the hazard taking place without the addition of the SIS, right? So you're saying that even if I don't install the SIS, what will be the frequency of the hazard? Okay. So once you determine all these parameters, it's easy enough then to go through, right? For example, you start here, you say that my consequences now is, for example, is CB, right? Exposure time, let's say it's right less than 0.1, right? FA, right? I have all the conditions met to do to take PA. I can probably avoid it, right? And my demand rate without the SIS is W2. Then we can say it's a still A. Still A basically still lower than still 1. Right? But if your consequence, for example, is here, right? Okay, it's CC, for example, CC, right? Because of you have a large release, for example, right? And if you take the same factors for exposure time, FA and PA, right? And the same demand rate, you get a one. Okay. Right. So again, once you've defined all your consequences, your demand scenarios, you discussed it, you've written that down, or what other safeguards are there in place, then looking at the table is easy enough to determine which parameters are required, right? As long as you have the consequence defined, right? And from the consequence, you can look at exposure probability, how often are people there, probability of avoiding hazardous event, and then the demand rate. Okay. All right. So the risk graph that you saw just now is a example for personal injury, but you can also do risk graphs for asset loss and environment, right? So you can also assess the impact to people, impact to environment, and impact to asset. And some companies will go also assess impact to reputation. So one way to remember is PEAR, pair, like the fruit, right? People, P, environment, E, A, asset, and R, reputation. Okay, so you can also generate risk graphs for asset loss and environmental impact. So it's important that once you assess the scale for personal safety, asset loss, and environmental damage, for example, right, the function should be designed to meet the highest integrity level. Okay, so if you get a SIL 1 for personal safety, a SIL 1 on asset loss, and a SIL 2 on environmental damage, right? You should design the function to meet a target of SIL 2, the highest SIL, right? Because of the 3. Okay. Okay. Let me quick time check. It's 3 o'clock. You guys want to take a break before 2-minute break, toilet break before I continue? Or do we continue?
That's okay. Can have
Okay.
break.
Break or no break?
Yeah, I think better 5 minutes break.
Yeah.
Okay.
Let's,
Yeah.
Can
5 minutes. All right.
let's take a
Come
5-minute
back
break.
at 3:05. 3:05. Okay. Thanks.
All right. All right. Shall we continue?
Okay.
All right. Okay. We've had a look at risk graph. We've had a look at risk matrix. So let's look at LOPA. So LOPA, before I start, so LOPA is one of those methods that's quite popular in terms of self-determination. Right? So a lot of companies are adopting this method. It's the default, so not default, it's sort of the choice approach for most engineering companies. So LOPA, or Layers of Protection Analysis, is a powerful analytical tool for assessing the adequacy of a protection layer, right? Used to mitigate the process risk. Okay. So LOPA covers analysis ranging from being a little different from in terms of complexity of risk graph, right? So to a little short of full quantified risk assessment, right? So it's a bit more complex compared to a risk graph or risk matrix, but it's not too complex compared to a fault tree analysis or full quantified risk assessment. The other advantage of LOPA is that it builds on the HAZOP study, right? So when you do HAZOPs, a lot of the information from the HAZOP can be taken into the LOPA study. Okay. So LOPA in its basic form is based on the SIS model. Pretty sure most of you have heard this already, right? So for hazards to progress and develop into losses, there's multiple teasers or multiple barriers with latent failures that would need to fail, right? You have can be like control valve failure, right? And then in between there's an alarm and operator intervention failure, right? And they can also have a SIS failure, ultimately leading to losses. Okay, right? So LOPA at its most basic form is based on the SIS model form. Okay. So to do LOPA, the approach can be taken as follows, right? So based on the consequence, right, that you discussed earlier, you evaluate the severity of the consequence. Okay. You compare the severity of the consequence with a tolerable risk criteria, or TMEL. Okay, I'll touch that in a bit, in a little bit. Identify initiating events and frequency, right? And if the overall risk is greater than the tolerable risk criteria, evaluate barriers or IPL that reduces risk to meet tolerable risk criteria. Okay. Let's go through on the approach. Right. So earlier we've discussed about consequence, right? So you discussed in a workshop, you discussed with the team, okay, what are the consequences, whether it leads to fatality or people injury, whether it will result in asset damage, whether it result in a environmental impact. Okay. So based on the consequence, right, we will need to benchmark it against or determine the TMEL. Okay. For example, right, this is one example of a table developed for you to determine the target mitigated event likelihood, which is the number here. Okay. Target event frequency. Okay. Right. So for example, if we say that the consequence just now will result in a fatality, right? Right. And then the target mitigated event likelihood, or TMEL, will be 1e to minus 4. This will be your target risk reduction, right? But if the consequence can lead multiple fatalities, for example, in this example, then your target mitigated event frequency will be 1e minus 5. Okay, again, it depends on your consequence, right? Environmental impact, or whether it's severe environmental impact, or whether there's a massive effect on environmental, right? You will need to select which TMEL or which event frequency is your target. Okay. Maybe I'd like to ask Faludin. So by the way, I'm not sure whether Khalil does LOPA.
Yes, Mr.
Right.
Yeah.
So on the worst case is what's your targeted event frequency? Minus
Line
5?
minus 5. Yeah.
Minus,
So our
minus 5.
risk metric is 554.
Okay.
Severity and we only do it LOPA for the highest one.
Right. Okay, yeah. So right, so minus 5 means to say is we'll look at later what does this number mean. Okay. Right. So the next step just now was that to determine the initiating events, right? So you've discussed earlier in the workshop, okay, for the hazard to develop, failures must occur, right? A pump has failed to stop, a control valve has failed to function, and so on. A human error has to occur, right? So you have to put a number on how frequent these initiating events or demand scenarios is anticipated. Okay, right? Okay, so initiating is the minimum combination of failures or errors necessary to start the propagation of the incident sequence. Okay, it
Yes,
can be
so,
as
just to read this one, for example, the failure frequency event a year. So 1 multiplied by 10 over -1. For example, this will happen once every 1 year. Is it?
no. So 1 in -1 is 0.1, right?
Yeah.
So it's 1 in 10 years. That's one way of looking at it. 1 in 10.
Okay. 1 in 10,
What?
it will be so when you say 1 multiplied by 10 over -2, it will be in 20 years.
1 in 10. So 1 times 10 to -1 is actually 0.1. 0.1.
Okay.
So 0.1 is either 1 in 10, right? 1 over 10, right? So it's
Yeah.
1 in 10 times, or right, or 1 in 10 years. Right? So that's the initiating event frequency.
It will be once in 10 times or once in 10 years.
Yeah. So it's it's 0.1.
And if it, in place of -1, it is -2, it will be
1
1
in
in 20
100.
years.
If it's -2, it's 0.01. So 1 in 100, 1 over 100.
Okay.
So it's 0.1, 0.01, right? So 0.0 -2 is 0.01, 1 over 1 in 100.
Okay. Clear.
All right, great. Okay. So this initiating event table, different companies have different tables. Some take it from CCPS. Some companies like Shell, they develop their own tables because they have internal data, sufficient internal data to determine the failure frequency. Okay, right. So based on the initiating event, then you need to determine the failure frequency. Okay. All right. So once you determine that the failure frequency, then you need also to determine the IPLs or independent protection layers, right? So if you remember the Swiss cheese, right? So what other barriers are in place other than the SIS, right? That you can take credit for. Okay. Right. So for you to select IPLs, there's certain rule sets that you need to follow when doing LOPA. Right. So which we call validity rules. Right. So the IPLs need to be effective. Right. Effective means to say it's big enough, fast enough, strong enough. Independent, right? So it's independent of the initiating event. So it's does not share any common cause failure. The other one is auditable, right? I mean to say that the values that you take into consideration can be maintained and it can be evaluated that it can properly function. Okay. So if I were to put it in layman terms, right, effective, right? So effective, let's take an analogy of your rain gutter or your monsoon drain. So Malaysia, heavy rainfall, right? So you're expecting that the monsoon drains will be able to sufficiently, drain away the water so that it doesn't flood. Okay. But if you don't design the monsoon drain to be big enough, right? Okay, then it will not be able to prevent the flooding. Right. Another analogy will be your brakes on your car. Okay. Okay, you have a fast car, heavy car, right? But the brakes, the brakes that you design is inadequately sized. So when you need it to function, it's not strong enough to provide the braking force for you to stop safely. Okay, right? So that is what we mean when we say that the barrier must be effective. Okay, it's big enough, it's fast enough, it's strong enough. Right. Okay, the second criteria for validity rule is independent. Right, independent of the initiating event. If you say that for example, in the case of, you say that high pressure in a vessel can be because of a pressure control valve malfunction. Right, the barrier cannot be, the IPL cannot be that you rely on the same valve to close. Right, it's not independent. Right, it has to be a different valve that you need to close. Okay. So auditable, right? As with many things, if you look at the barriers, right? It's not, there's holes, right? There's latent failures, right? We need to say that these barriers can fail. So you need to make sure that the barriers or the IPLs can be maintained and evaluated that it can properly function. Okay. For example, if you take a barrier, a relief valve as a barrier, for example, you have to make sure that the relief valve or the pressure relief valve is maintained and it can be evaluated that it can properly function. You cannot take, for example, an equipment, this RV, as a overpressure protection, but you say that I'm unable to do maintenance on it. I just hope it works. Right? Then it doesn't become a valid IPL. Okay. Right. So this can be barrier validity sometimes can take a bit of a discussion during the LOPA workshop. Right? To determine whether it's effective, to determine whether it's independent. Independent may be faster, maybe easier, but anyway, and whether it's auditable, right? It can be maintained and evaluated if it can properly function.
Doctor, I have a question. Can you elaborate more on IPL? How to identify IPL, please?
How to identify IPL? There's an example later that we can yeah, there's an example. I think we'll go to the example. Okay. So an IPL can be a lot of things. It can be analyzers, it can be instrument barriers. For example, right, if there's a pneumatic interlock installed, then there will be an instrument barrier, right? That can be, heat tracing can also be considered a barrier, right? So there's a whole list of barriers that you can use. So this is just a snippet of an example from a company standard, right? Okay.
So it can be a safety critical device or
yes, yeah, yeah. That's a good point. So typically, for if you take credit for an equipment as a barrier, then most companies will then determine or classify that equipment as a safety critical device or safety critical element or SCE. An example of another alarms, for example, right? High alarms, low alarms, that can be taken as a barrier. Pressure relief devices, that's typical for you to take as a IPL, right? So these items, if you take it in a LOPA, needs to be maintained, right? Because it's preventing the propagation of the hazard. Then this would typically then be marked as an SCE item. Safety critical element. Okay. All right. So.
Okay, means we as an organization need to detect hazards, and from hazard study we can have loop study. So from that also we can identify the IPLs.
Yep. Yep. That's great. So if, for example, Ali, if you do HAZOP, for example,
Yeah.
you identify safeguards, right?
Yes.
In the HAZOP, those safeguards can then be brought into the LOPA study to determine whether they are valid IPLs. Because during HAZOP, you do not go through the rigor testing of whether it's big enough, whether it's auditable, whether it's independent. Usually it's just, identifying all the safeguards. But the LOPA is where you determine whether it's a valid, the safeguards identified are valid and to be taken as valid IPL or independent protection layers.
LUBA is validation then, huh? It is a validation for the for the hazard scenario.
For the, so you validate, so you can essentially you're taking the safeguards from HAZOP and you're seeing and you're testing it whether they are really independent or they are really valid IPLs for use in LOPA. That's why I said earlier that the LOPA is actually it's an extension and it builds upon the things that have already been discussed in the HAZOP study.
Okay, and if I already identify hazards using bow tie technique, so I will identify IPLs here.
Yeah. The bow tie technique is a visualization of the LOPA method.
Okay.
Yeah. So it's one way to visualize LOPA.
Okay, we visualize LOPA by use bow tie, right?
Yep, you can do that.
You can do that. Okay, thank you very much.
Okay, great. Right, all good questions. Okay, so one thing to note is that these IPLs or the barriers or protection layers, again, if you look at the Swiss cheese theory, they can fail, right? They're not it's not that they will not fail, right? So then you need to determine for each barrier what's the probability of failure on demand. Okay, what's the PFD? Right? What is the likelihood of it failing? Okay. So based on MTBF, so 1 in 5 years, 1 in 10 years, 1 in 10, 1 in 10, 1 in 100. So each company will have its own PFD table, right? There's some generic ones that you can use from CCPS, right? But there has to be a standard number that you use across your LOPA study. Okay. And again, when we talk about IPLs, remember it has to be maintained, right? So this number will need also to come with a minimum test frequency to obtain the PFD credit in LOPA. And say how often you need to do maintenance on these barriers for you to take credit of this PFD, right? Okay. For example, right, if you want to take heat tracing, for example, you want to take that 0.01 probability of failure on demand, you have to do a minimum yearly heat tracing based on this example here. So again, each company will have to determine what will be the failure rate they want to take and what will be the maintenance regime that they are willing to take on. Okay, let's look at an LOPA example. So again, in the setup, you have a pressure vessel, feed coming in, 50 bar gauge. There's a pressure control through the overhead with the RV to flare. Okay, controlling this control bar. Okay, there's a level control bar here, right? So let's say, for discussion's sake, that the consequence of overpressure of this vessel is a vessel rupture leading to loss of primary containment, LOPC, and then explosion, resulting in explosion, right? Resulting in up to 3 fatalities, 1 to 3 fatalities. Okay, right? So if you remember the based on the consequence, we need to determine the consequence severity, right? Identify the consequence severity. So based on the vessel rupture and LOPC and the explosion, we say that it's in this case it's a severity D, right? With the TMEL of 1 times 10 to minus 5, right? Because you have a lot of fatalities, right? Okay. The second step is identify what can cause a high pressure. So we can say that this control valve control failure PIC. So this pressure control is supposed to maintain the pressure inside the vessel, but let's say it malfunctions, it opens more than required, then you can have more pressure into this vessel, resulting in an overpressure of the vessel. So one of the initiating events we can determine is the control valve failure or PIC failure, which is 1 times 10 to minus 1, right? Which is 0.1. Okay. So, okay, this is where, Ali, you mentioned bow tie, right? So this is where I think it will look very familiar to you, right? So if you were to put this in a straight line, right? So control valve, control failure, okay, right, is 0.1, right? 1 times 10 to minus 1, okay? So what other barriers are in place that you can take credit for? Example, right? So you see that there's a relief valve here, relief valve to flare, okay, that you can take as an independent protection layer. So it's independent, it has nothing to do with the pressure control valve, right? It's big enough. Let's say it's sized to sufficiently relieve the full capacity of the vessel, right? And it's auditable. There's track record that the RV is maintained, right? And you can do maintenance during your turnarounds, okay? So you can put one safeguard here, one IPL here. So it's fully rated, say clean service. Then you say the PFD here is 0.01, which is 1 in 100, right? So PFD average is 0.01. Okay. And let's say you have another barrier that you say that we can take is the fire and gas detection. When there's a vapor release, there's gas detectors that will detect there's a release that you want to take at 0.1, right? Which could be mitigative before the fire and explosion case. Okay. Right. So if you multiply this, right, 0.1 times 0.01 times 0.1, what do you get? Kai? 0.1 times 0.01 times 0.1. Nabila.
It will be once every 1,000 year.
Yeah, once in 1,000, right? So there will be 1 times 10 to of minus 4, right?
Exactly.
10,000. Yeah. So this is minus 1, this minus 2, this is minus 1. So minus 4, right? 1 in 10,000. 4 zeros, right? So, but you know that based on the consequence that we determined just now, your target mitigated frequency is minus 5, right? So there's right. So there's a gap of 0.1, right? Between your target and your overall intermediate event likelihood, right? So you need to add, you're missing 1 0 here, right? So this is 1, 2, 3, this 4, minus 4, but your target is minus 5. So there's a gap of 0.1, right? So if you remember,
But it should be, yeah. So we can add additional control over here, or
yeah. So you can, so that gap is actually your target seal.
yeah.
So if you add a seal 1 function, because remember seal 1 is between 10 to 100, right?
Yeah.
Yeah. Farudin, you have a question?
Yeah, Doctor. Actually, looking at this, if we follow through the whole local step, there's another that we haven't completed yet, like the enabling conditions, how probability of the vessel rupture, something like that. And the other is
Correct.
so modifier.
Yeah. Exactly right. Exactly. That's if you were to do actual OPA, there's conditional modifiers that you can take: probability of explosion, likelihood of vessel rupture, whether it's based on the pressure difference, pressure ratio. Right. Yeah. Exactly right. Fadil. I think if we were to do an actual OPA, it would be much more factors that we can consider. But for the sake of brevity, for this example, I've not taken it for now. But you're right, exactly right. We can take a few more conditional modifiers. Okay, right. So depending on the gap. So now what we're saying is that if we put a still 1 function here, right, and we take a PFD probability of failure of 0.1, then you can meet the target mitigated event likelihood of -5, right? Because this is, you multiply all this, 0.1 times 0.01 times 0.1 times 0.1, it will be 1 times 10 to E minus 5, 10 minus 5, which is your targeted mitigated event likelihood. Okay. Right, and as I've already mentioned, if you do LOPA in actuality, there's a lot more factors that you need to consider, or what we call conditional modifiers. Right. Example, what is the probability of explosion, right? So we said just now that not all gas releases will be ignited leading to explosion. It could be 1 in 10 cases or 1 in 5 cases, depending on the product, depending on the rate of release. Okay. There's also other conditional modifiers. For example, not all overpressure case will result in catastrophic damage to the vessel, right? Whether it's 1.5 times or 2 times or 3 times the design pressure. Okay. Right. So it can be very complex to do LOPA, but fundamentally it's about taking into consideration your target, taking into consideration your available barriers or available IPLs, right? As well, you can also take into consideration things, other conditional modifiers, right? And the gap between your intermediate event likelihood and your target will be your target field. Okay. All right. Arden, thanks for that.
So the target after LOPA, we shouldn't have. You can see we might have an accident, but the possibility will be very high. Well, very low. Sorry.
Very low, yes, yeah. So it's not perfect. I mean, it's about reducing risk to a tolerable level. You cannot eliminate risk, but you want to make it such that it's tolerable.
Actually, the problem we haven't seen like a kind of linking the HAZOP study with LOPA in a practical way in the industry like till now. I haven't seen this one. You can see, but we do have like some kind of challenge in some systems where we are like looking for some system to just address the risk if it is tolerable still, or still we need to take this risk or no. So it's LOPA is good for that, but as I told you, in practical, I did not have like I haven't seen this kind of practice in place right now.
Right. So maybe that's something that you might want to consider. If you have already HAZOP in place, you can use whatever knowledge that's already been discussed during HAZOP study to bring into a LOPA, for example. Then from LOPA, then you can determine what functions that is actually required and what SIL levels are needed for your safety functions.
Yeah, we use the bow tie, which is a visualization for LOPA. We use a bow tie. So what we do is actually we try to identify the most significant risk at the plant, and then we took those risks and conduct a bow tie, and then from the bow tie, the outcome we just consider it as actions. We just avoid this step by going directly to bow tie.
Okay. All right. Okay. Yeah. I mean, if you do bow tie, it's actually LOPA is about then putting the numbers to the bow tie, assigning the numbers, and then
but as you know, bow tie is not quantitative; it's qualitative. I feel it is. If you do LOPA, then you will have like a kind of quantitative, assessment.
Semi-quantitative. Yeah, exactly. Okay. All right. Hope that was okay. Quite a lot to cover. How much time do you have? 30 minutes. Okay. Let me try to breeze through the rest. Okay. The other thing to talk about is the success criteria. So success criteria is sort of the statement that defines when the sensors have successfully detected the hazardous situation in the initiating event, right? So for example, in this case, you can have 1 out of 1, right? In this case, PZ, pressure trip. 1 must detect to trigger a trip. You can have 2 out of 2, right? In this case, both must detect to trigger a trip. Or you can have 1 out of 2. We need to say either one. If either one detects, then it will trigger the trip or the automatic action. Okay. Maybe just a question, if anybody. So from which these 3 architectures, 1 out of 1, 2 out of 2, or 1 out of 2, which one do you think have the worst probability of failing on demand, worst, and high probability of failing?
So actually, there are two. I mean, having the architecture voting, either it's good for reliability or good is in terms of safety. For good in terms of safety, especially to avoiding the dangerous failure, there's supposed to be the one out of two is better in terms of safety, because we have the backup of the redundant system, but only one trigger that will trip the system. So that's the good for the safety, but it's not good for the reliability. So that's the things that we do. And the worst for the safety is the 2 out of 2, but it's good for the reliability. That's the different thing.
Yeah. On the money already. Yep, exactly right. So 2 out of 2 is it's nice to keep the plant running. Meaning, say if they have one transmitter is faulty, right? It does not trip the plant, but then that also means that it will not trip in terms of safety. It will be not so good because then it will not trip when required, if one is faulty, right? Because you need both to function correctly, right? 1 out of 2 is more favorable from a safety standpoint. If either one detects, then it will initiate the automatic action to shut down the plant. But it's not so good for plant reliability. So let's say one gets struck by lightning or there's a failure, then you might have nuisance trip. Okay.
Yeah.
Right. So that's
the other SFT also is very good for one out of 2. SFT is one, but very for
yeah, correct. Fault tolerance. So 1 out of 2 from a safety point of view, I think safety engineers like it very much. Right. It's very safe. Right. But yeah, I think the other thing to consider is the probability of it leading to false activation or nuisance trip. Okay. So some companies put the voting on their PNIDs, right? So it's easy for you to determine what's the success criteria. Some companies don't put it. It depends. So in this example, in this particular example, this company decides to put all the voting on their PNIDs. So you know that between these two level trips on this particular vessel, it's a 2 out of 2 voting. Okay. Right. So both must show high for you to trigger the automatic action. Right. Similarly, there's also success criteria that needs to be determined for your finite elements. Okay. Right. For example, here, 1 out of 2, right? Either one must close. So if it's a fail close valve, so imagine you're trying to stop flow from left to right. Okay. For you to stop the flow going through, is closing one sufficient, or must you close both valves for you to stop flow from going from left to right?
One
is sufficient, right? So just closing one, right? So
One.
either one valve must close, so that hence why there is one out of 2. Okay. So if you take, for example, in this example, FC fail close, right? Again, from left to right. If you want to stop flow, right? Is closing one sufficient, or must both valves close?
Now both, because each one going to the different location.
Yeah. Right. Okay.
The right side.
Yeah. So both valves must close. Hence, both valves must close, right? So this success criteria is important for you to determine based on the setup of your plant, right? It's not one size fits all. It depends on how whether your valves are fail closed or fail open, whether they are parallel lines, they are series lines, and what's the hazard you're trying to or mitigate. Okay, so this is also required for you to identify, ideally during the still classification. Okay, right. For example, here, right, fail close, right. It doesn't say whether it's 1 out of 2 or 2 out of 2. There's something that you have to determine for fail close, and closing either one will be sufficient. Okay. let's look at this exercise. Maybe just have a look at the setup. Think about this level low. Okay. Right. What would be the design intent of this level low? Right. What are the demand scenario? What will be the consequence and success criteria?
I think Lolo should trip the bomb.
Okay, that would be the design intent. So design intent and demand scenario. What's the design intent?
This is the design intent that, for example, low alarm will trip the bomb. Low will demand scenarios, maybe because of low, maybe there is like kind of vacuum will happen to the tank itself. So we might need to introduce like rupture disk to the tank to avoid tank going for the damage.
Okay. All right. So consequence I hear tank damage. Any other consequences that you think might happen on level low?
You can see pump damage, dry run,
Pump damage, dry run.
High pressure, low pressure interface, then will be if the vessel is high pressure, then we end up with the downstream of the pump.
Right. Okay. Success criteria then what would be the success criteria for the level?
ROP should be closed when it's detected with the low level before loss of the level.
Yeah. So okay. Let's look at the. Okay, so design intent on low level, protect the pump from running dry. Right. That could be one of the design intent, right? Depending on the parameters here. Okay, so the demand can be because of loss of control. Maybe there's a level here that you lose control. Okay. And then the consequence here is, as you say, could be pump damage because of pump leakage, pump dry running, right? Okay. Maybe you have possible injuries or local damage. Right. Again, this is a consequence can be debated in the workshop. Right. Success criteria will be the low level will be 1 out of 1. And then the tripping the pump will be sufficient for it to stop the pump damage. Right. Okay. This will be one example. Again, this will be one of the things that we need to discuss during the workshop. Okay. All right. 15 minutes left. Okay. I'll just breeze through. Okay. So with
Can we go back to the previous sketch of the simplified diagram? Sometimes when I conducted the low power stations, we can see that in here there are two shifts, but having the sharing of the sensor and sharing of the final element. Sorry, not different final element, but sharing the sensor. The quiet debate is it okay to have we calculate at the two different SIF and then we can take credit for those two different SIF, or we just say that cannot this is the one SIF because the sharing is sensor. So the debate is quite frequently during
right. So I think to that end, that's why it's important to determine the design intent. So the different shifts, if you have the same design intent to protect the pump, then it might be the same shift, right? But if it's although it's different sensor, but if the design intent are different, then it might be then more logical to treat it as two different shifts. Right. Again, probably I think you're right. So sometimes, for example, that you can have different sensors. One is flow, one is temperature. But it could be that the design intent is to protect the equipment, a reactor, for example. Then you might say that actually then, although it's two different sensors with two different measurements, that maybe it's a one shift. Right. So yeah, so it's a discussion to be undertaken during the low power workshop, and that's where a lot of the valuable discussion and valuable input from process, from instrument, from operation, from maintenance is required to be consolidated.
Yeah, and quite hard discussions. In the fact, the percent transmitter or level switch for this one, let's say only take credit for the seal one, let's say, But somehow, if we taken two different SIS, then we may have the two created for different seal level. So like we have two SIS with each of the seal one, but somehow the center only created for the seal one. So that's yeah, that point. That point is the debate around this.
Yeah. Okay. All right. Thanks for that. Okay. Thanks for that. Okay. We have about 15 minutes left. Let me see if I can power through this one. Okay. So SIS failures and reliability. So SIS is not immune to failure. It's also prone to failures, right? The safety systems, right? There's two types of failures. One is safe failure, right? One is dangerous failure. The difference between the two is that safe failure is that it can potentially cause the process to achieve or maintain a safe state, right? Meaning to say, when it fails, it trips the plan. It's everything safe, right? So that's what we call a safe failure. A dangerous failure is the failure affecting the equipment within the system, which causes the process to be put in a hazardous state, right? Or puts the system in a condition where it may fail to operate, right? This is called a dangerous failure. It's supposed to trip, but doesn't trip. That's a dangerous failure. Okay. The safe failure is that it's not supposed to trip, but it trips, right? So you have a nuisance trip. That's a safe failure. Okay. So let's look at the example. Okay. So, right. So there's a level here with a level higher here. Okay. If the level is okay, it's okay. But level increase more than a high set point, it trips. This is okay. This is what we want. Okay. Dangerous failure is, right? The level is below the high set point. But then the level, when it is above the high set point, it does not trip. It still treats as an okay condition. That is a dangerous failure. That's not what we want. Right? A safe failure is the level is normal. It's way below the high level trip set point, but it trips. Right? This is a safe failure. Means that it trips early, or it trips when it's not required. This is considered a safe failure. Right? A dangerous failure is that it doesn't trip on demand. Supposed to trip, but doesn't trip. Right? So when you do safety system, there's a fair bit of calculation required based on the failure rates, right? So failure rate, when you look at the datasheet, is expressed in lambda or FIT, failure in time. So there's 4 parameters that you need to look at. Lambda S stands for safe. Lambda D stands for dangerous. So SD stands for safe detected. SU stands for safe undetected failure rate. And DD is dangerous detected, and DU is dangerous undetected. Okay. So the sum of LSD and LSU, right, is basically the failure rate, safe failure rate. And the sum of lambda DD and lambda DU is your dangerous failure rate. Okay. So why is this important, right? Okay. So this is again from SysTech, right? Taken for the UTP slide as well. Okay. So the safe failure rate, right? There's also a portion of it is dangerous undetected, right? And so there's a portion of it from this failure rate is dangerous detected. Okay. Right. So safe failure rate, we are okay, right? Because it trips early, that's fine. It's more to reliability issue. Okay. Dangerous detected failure, right? When you say detected, it means that it's detected by diagnostics, right? Your equipment has self-diagnostics. It can do self-tests. It will detect what failures has occurred, right? That will be covered under dangerous detected. Okay. There's still failures, remnant failure that's undetected. Is that it's undetected by diagnostics. One way to reveal the failures is by doing maintenance or proof testing, but that still doesn't cover all the dangerous undetected failure. There's still a small portion of dangerous undetected failure, right? Unfortunately, it can only be revealed through incidents, right? Right. So the aim here is to reduce this dangerous undetected failure as much as you can, either through diagnostics, right, increasing diagnostics coverage, or by revealing more failures through proof testing. Okay. if you open the certificates or the failure rate data from manufacturers, right, the failure rate is always expressed in FIT, right, which represents failure rates and how many failure occurs every 10 to the power minus hours. Is in hours, right? So 67 FIT, right? So it's 67 per 10 to the power of minus 9 hours. Right. So this the lambda is always in hours. Okay. The failure rate data, where do you get it? Right. In this example, it's from the manufacturer. But you have to note that the failure rates may differ depending on the sources that you take the failure rates from. So among sources of data that you can take is the internal data. So big companies like BP or Shell, they are big enough to have their own internal failure rates taken from their manufacturing sites. They may generate their own failure rate data. Okay. The other source of data is from generic industry data. So there's organizations like Oreda or Syntef, right, that takes this data from various companies, from BP, from Shell. They're independent organization. They take it and then they create a handbook of failure rates. Right, these are published industry data. Okay. Or the other source is manufacturer data. So manufacturers will do their own lab testing. Will have their own records from clients, from customers, and they will publish their own failure rate data. Right, and the quality of the data may differ depending on where you are. Okay. For example, right, the generic industry data may be conservative. Right, you say that the failures can be 1 in 20 to 1 in 50 years. Right, may be conservative. Manufacturers may have more better numbers, optimistic numbers, right? Right, and some manufacturers may have really optimistic numbers. So it's important for you to look at the data and determine what sort of data that you want to use in your safety systems design, right? Okay. Faridin, your Cargill has their own internal data, or you guys are using generic data?
No, we use generic from CCPS.
Okay. Okay.
But you got killed.
Okay. Okay. Right. So we've covered analysis. We've covered we're now covering about operation maintenance. Like I mentioned earlier, this is one of the longest phases. Right. So it's important. Remember, when we take IPLs, it has to be maintained, right? Same like safety systems, you have to maintain it. Okay. Maintenance activities, there's a few approach to doing it. So there's reactive maintenance, that you wait until it's broken and then you fix it, or some call it run to fail. You don't want to do this with your safety systems, right? You don't want to run it until it breaks. Preventive maintenance, right? You do it because it may break based on then you better fix it anyways. Or the other one is predictive maintenance. You know when it's expected to break, so you plan for that. This one requires a lot of data, right? Okay. So you want to make sure that you have routine maintenance for your system, because you want to make sure that it's safe, it's capable to operate on demand, right? You know, the maintenance that you can do is simple things like cleaning, depending on where you are, there might be dust ingress and all that, lubrication, calibration, and then measurement accuracy of your process sensors, right? Okay, so you have to make sure that you look after your SIS, because you are depending on the SIS to actually look after you, to act automatically to prevent or mitigate the hazard. Okay. So why do we do proof testing? Right. So again, function safety is about achieving SIL, and SIL is based on, if you remember, the PFD average, right? So you want to maintain the PFD average. Okay. Right. So as equipment performance, any equipment will degrade with time, and as it degrades, your probability of failure on demand also will increase. Okay. You want to also make sure that you do regular maintenance to detect and repair failures, to make sure that your PFD average is sustained. And every so often, you want to make sure that your equipment is restored to as new condition. Bearing in mind, it's the same as your brakes, right? And on your car, every few hundred kilometers, you want to make sure that you service your brakes. Why? Because you're depending on it to keep you safe, right? Okay. And then after a while, you need to change your brake pads, for example, to as new condition. Okay. All right. So quick look at this. So if you look at example at the proof test, right? Whenever you do whenever you do testing, right? So what happens? Okay, let's say you're here, right? As time goes on, right? This line goes up. This is your PFD average, right? Your PFD average. Your PFD average goes up. Okay. So when you do your next test, your next maintenance, you actually bring your PFD average back down. Okay, assuming you do a perfect testing. Okay, right. Same here, right? If over time the probability of failure goes up, but when you do your test interval or your proof test, it sort of brings down the PFD average back down. Okay, right. But again, if you remember that the proof testing, there's always that small sliver of dangerous undetected failure that you're unable to detect with proof testing, right? So proof test profile. So in actual fact, when you do your testing, right, PFD goes up, and then when you do your testing, it might not uncover all the dangerous undetected failure, right? So it doesn't go all the way down. Okay, and then it accumulates over time. So between the next testing and this testing, it also goes up, and you do another proof test, but you might not uncover all the proof tests, all the dangerous undetected failures. So it goes down, but not all the way. Right, and eventually it goes up, and then it goes from SIL 3 band to SIL 2, and then becoming not SIL rated. Right. Okay. So CPT here is coverage of proof test. Okay. So it's important to make sure that your when you do your testing, it uncovers as much possible failures that it's possible. Okay. And how do we do that? It's by generating a test procedure. Okay. The specific test procedures is required to be developed for the safety system. Okay, and this test procedures will be used by maintenance and to do the testing on the sensors to see whether it's functioning as required. Right. For example, if you do maintenance on the analog sensors, right, you can do 5-point calibration check, check safety parameters on the transmitter, whether there's delays, there's and so on. Right, make sure that the right protect is active, and you can do inspection to make sure there's no corrosion or there's no water ingress or whether it's still in working condition. Okay, same thing for discrete sensors for switches, right? Okay, these are general steps. I think if you're into operation and maintenance, you will be familiar with this already. Okay, I'll skip this one now. This is a sample of a proof test check sheet, right? A check sheet that you can give to maintenance so that they can do inspection on site, right? Do visual checks, check for sensor that is trending okay in the DCS, right? If there's a hardware right protection, whether it's still there or not, right? Simulate the process conditions, see whether it's reading correctly, accurately, okay? And if needed, right? You want to bring it to back as new condition. You might want to overhaul or replace the equipment. For final elements for valves, it will be similar. There will be things like visual inspection. You can do things like interlock tests, see whether the valves are closing and opening as required based on the conditions of the logic. You can also do rebuild, right? Leakage test, right? The valves, if it's closed, is it fully tight? Is it stopping the fluids from passing through as required? Okay. There's also some of the tests that you can do for finite elements, right? Again, visual check, interlock check, right? If the valve is supposed to close on pressure high, you need to test it. right? Once a year, once every 3 years, once every 2 years, depending on your target sale, right? Overhaul, right? The valves can be in service, but then every turnaround, for example, you need to bring it down and inspect internal of the valves, whether it's still functioning as required, whether everything's okay, or whether you need to replace the soft parts, right? Okay, I think that's the end of my slide. Oh, yes, ngam 4 o'clock. All right. That's the end of my, any questions from the team here? I think I've been rambling for two hours.
Yeah, questions.
Right.
A couple of questions. Can you hear me?
Yeah, can.
Yeah. First questions. I've experienced dealing with the consultant and need to get the LOPA, and for one of the facility, actually that for the LOPA revalidations at the beginning of the project during the project facility, seal determination using the risk graph, and then after several years, 5 years, the validation, the assessment for the ACT facility, part of the PSC validation. But we use the LOPA method, and in general, the result is the risk graph is more conservative compared with the LOPA in general. So, is that the common that maybe you found in several areas, but at least for the several note that we assess, risk graph is more conservative compared to the LOPA. Is that something that typical that you found in some of the facility? That's the first question. And the second question is about the conducting the seal verification. Is it okay if we use the different tool? Of course, several companies have the tool like the Exida, seal verification, or maybe ADB. First verification using the tool A, and then the second one with the tool B. So is it good approach? Because of course behind that tool there will be the different source of the failure rate, as you mentioned, of the FID, or the source of the FID. So what's the actually you said yourself? If you use the different tools, is it okay or supposed to be not, because we can compare, we can compare level between the different assessments.
Yep. Okay. All right. Thanks for that question. So I'll, if I understand correctly, the first question is about risk graph. You're doing a project from risk graph, and then a few years down the road, you want to do seal determination, but instead of using risk graph, maybe you're using a LOPA approach. And then the general finding is that the risk graph is more conservative, meaning to say that the risk graph tends to yield a higher seal compared to LOPA, correct?
Yes, correct. The finding.
Yeah. Okay. Yeah. So I'm sharing my personal experience. So my experience is somewhat similar to you, Farudin. So again, if you look at the risk graph, fundamentally, you look at the risk graph. There's not a lot of the parameters is predefined, right? So so there's only so much that you can take into consideration when doing risk graph. What I concur with your experience as well, that when we do LOPA, because when we do LOPA, it's somewhat more quantified than risk graph. So you can also take into consideration conditional modifiers, right? Things like likelihood of explosion, probability of ignition, and other factors like likelihood of probability of the vessel rupture and the severity and all that. So typically it yields a lower seal compared to risk graph. In some cases, but at least by factor of 1. If not the same, if by 1 factor lower. I mean, if you use the risk graph, you might get a seal 2. If you use the LOPA, you might get seal 1, for example. That would be my experience as well, similar to you already. Okay, so I think that's also part of the reason why LOPA is a bit more preferred more and more engineering companies. Because when when you do engineering design, right? When if it's lower seal, then actually your design cost to implement the SIF will be lower than if you as opposed to RISC-Graph. Hence, there's also companies that when they migrate from RISC-Graph to LOPA, is that they say that you use RISC-Graph, but any functions that result in a SIL 2 or higher from RISC-Graph, you bring it to LOPA to determine whether is it actually SIL 2 and or does the LOPA then determine that actually the target say is SIL 1. That's one way other companies are doing it that I've seen, right? In between. Yeah. Okay. So the other question here from you is on the verification, right? So about quantification of the PFD average, right? There's many tools in the field. Excellencia, you can do manual calculation. You can do fault tree analysis, FTA. So yeah, personal experiences. I think is that if when you use these two different tools, the result can be different. I mean, the PFD average numbers will definitely not be the same, because some will use Markov model, some will use the basic formulas in the IC, right? And some will make certain assumptions, right? Some tools will not allow you to take credit for proof test coverage or diagnostic coverage. Tools from Exida, for example, will allow you to make assumptions on proof test coverage, right, of 90% or 70%, right? Hence, the PFD average number will be different. But because the SIL band is actually fairly large, right? For SIL 2, for example, it's between 100 to 1,000. Right. Definitely, I think the numbers will not be the same, but I would think then that the overall result will not be that much different in terms of SIL band. It should be still in the same SIL band. If it's vastly different, then we have to really check on why is that so. Does that answer your question, Rory? So, example, if you do verification, if you use verification using one tool, you get SIL 3, and then you're using the other tool, you get SIL 1. Then it's too big of a difference. That might be some human error in either one. Right. Yeah. So I think the popular tool now is Exida. I'm not sure what Cargill is using. Yeah, but I've seen some companies even using Excel. But that's their own internal tool.
Yeah, to be honest, in my kind of organization, we are not really on that approach yet. So it's better in my case.
Okay, good. All right, good question. Thanks. Good question. Thank you. Any other questions? No. If I guess I'll put my email in the chat. You guys can email me. There's no chat here. Yeah, maybe you can ask from Dr. Bawadi. Okay, back to you, Dr. I think you're on mute.
Can you hear me?
Okay, right.
Yeah, thank you very much, IR Fashan, for giving the the lecture on Saturday afternoon. I know it's very tough. Both the students and also to the lecturer as well. So if there is any question, I can read out for IR Fasha, because I can see all the chat here. If you have final questions. No? Okay, there's no questions from the student. Just let you know, next week we have quiz. Quiz you can do online. So, and the lecture also be given to you lah. Maybe after this, Fashan can email me the lecture notes lah, the lecture for these 2 sessions. With that, I end the session. Thank you very much, both Fashan as well as the students. See you again, inshallah, next time. Bye. Assalamualaikum.
Waalaikumsalam. Have a good day, everybody.
Have a good day. Bye.
Thank you, Doctor.